Welcome back. Today we're going to be working on uniform and non-uniform probability. Our content objective is students will be able to find the probability of both a uniform and non-uniform event. Language objective is students will be able to discuss whether a situation is uniform or non-uniform in terms of probability. Why am I learning this? Well, it's important for real-world examples like finding out whether your favorite sport team is likely to win. So background knowledge, we've discussed this before. Please understand probability can be expressed as a fraction or sometimes a decimal between 0 and 1. 0 being impossible, 1 being for certain. But we can also express it as a percent. Once again, 0 being impossible and 100% being for certain. There's a couple of vocabulary words that I really want you to remember for today's lesson. Experiment. An event is an experiment. An experiment is an activity which results from observed. Each experiment is called a trial. Okay, an outcome is the possible results of the event. But the main thing I really want you to remember is sample space. Sample space is the set of all possible outcomes of an experiment. So if the experiment was flipping a coin, the sample space would be heads or tails. If the experiment was rolling a number cube, the sample space would be 1, 2, 3, 4, 5, 6. Again, it's all possible outcomes. Probability, it basically describes the likelihood of an event occurring. We usually describe it as the number of desirable outcomes over the total number of outcomes. Theoretical is what should happen, and experimental probability is what ends up happening. Okay, so there's a difference there. This is what we expect to happen, and this is what actually does happen. So in this case, the event is spinning a spinner. Okay, do you notice that all sections of the spinner are of equal size? Okay, this spinner is an example of a uniform probability, where each outcome is equally likely. So 1 is likely to be as spun as a 2, 3, 4, 5, 6, 7, 8. All of them have an equal chance of getting spun on. Okay, so uniform probability by definition is a probability model where each outcome is equally likely to occur. Now notice spinner B, I went ahead and made 1 just a little bit larger. Okay, it's twice the size now of 3, 4, 5, 6, 7, 8 because it took the place of the 2. So here, notice section 1 is twice the size of the other ones now, so it's not as equal. So this spinner is an example of a non-uniform probability. Basically, all the outcomes are not equally likely. In fact, section 1 is twice as likely to be landed on than the others. So by definition, a non-uniform probability is a probability model where each outcome is not equally likely to occur. So if you're thinking about a game, this would be unfair because 1 would have a more likely chance of getting spun on. But if you compare it to spinner A, let's go back real quick. If you compare it to spinner A, each number is equally likely to be spun on. So with that said, let's go ahead and try an example. Our experiment here is flipping a coin. That's the event. Okay, well, first let's consider the different possibilities. 1, it can land on heads or it can land on tails. So the sample space is heads or tails. Do you think this is a uniform or non-uniform event? Hopefully your answer was uniform. So that would be part of the question. Is it uniform or non-uniform? And the next part would be why? Well, to explain, I would say it is uniform because heads is as equally likely to be landed on as tails. So because there's an equal chance of it landing on both, it is uniform. So again, on your homework, you're going to be asked to state, is it uniform or non-uniform, and then why? So one way of determining whether it is uniform is by asking yourself, okay, well, what is the probability of it landing on either side? If they are equal, then obviously it's uniform. And if they're not equal, then they are non-uniform. So here I would say it's 1/2 land on heads and 1/2 probability of it landing on tails. And since it's the same, it is a uniform probability. Now let's think, how could you make it so that it's a non-uniform probability? So how could you change this event so that it's not as equally likely to land on heads or on tails? Think about that. So some possible answers might say, weight the coin, make it heavier on one side than on the other so it can land on one side more than the other. So that's a possibility. Okay, moving on to another example. So here the event is to toss a number cube. Okay, so before we talk about if it's uniform or non-uniform, let's quickly talk about the sample space. The sample space, just a quickly reminder, is all the different outcomes. So the sample space would be 1, 2, 3, 4, 5, or 6. So the question is now, is this a uniform or non-uniform probability? Is there an equal chance of me rolling the number cube and landing on a 1? Is that the same as rolling a 2, a 3, 4, 5, or 6? Or is it more likely to be rolled on one number than another? Hopefully your answer was uniform. Okay, so that's going to be part of the answer, but the next part would be, okay, well, how do you know it's uniform? Well, to explain why it's uniform, you should be saying because it's equally likely to land on a 1, on a 2, 3, 4, 5, or 6. They're as equally likely to be landed on when you toss a number cube. So once again, to answer that question, if you think it's uniform or non-uniform, you can ask yourself, well, what's the probability of landing on any of the numbers? Okay, so for 1, it should be 1/6. Rolling a 2 would be 1/6. Rolling a 3 would be 1/6. Rolling a 4 would be 1/6. Rolling a 5 would be 1/6. Rolling a 6 would be 1/6. So hopefully from that, you're able to determine, okay, well, they're as equally likely to be landed on. So for those reasons, they are uniform because there's an equal chance. That is the key word. There is an equal chance of it landing on any of the numbers. Okay, but now what could we possibly do so that it's a non-uniform probability model? So make it so that it's not an equal chance of landing on any of the numbers. Well, there's different answers. Mine might be, okay, well, I'm going to change the 2 on the number cube into a 1. So now it's not equally likely to get a 1, 2, 3, 4, 5, 6. I'm sorry, a 1, yeah. Because now 1 is more likely to occur. So now let's take a look at tossing a cup in the air. Do we think it's a uniform or non-uniform probability model? Well, real quick, let's take a look at the sample space. If you were to toss this cup in the air, there are 3 different outcomes. It can land with the opening on top, or it can land on the bottom, or technically it also can land on its side. So hopefully you guessed non-uniform. Okay, why, you might ask? Because it's not an equal chance of it landing on any of those outcomes. They're not as equally likely to land on the open top, the bottom, or the side. So remember, on your homework, you're going to be asked to also explain. So the key word is to say that it isn't an equal chance of it landing on the different outcomes. So in this case, the open top, the bottom, or the side. And again, you can ask yourself this question, do you know the probability of it landing on any part of the cup? Actually, my answer is I don't know, and the only way I could determine that is by conducting many trials of the experiment to know the approximate probability. Next, what if we were to throw this slice of peanut butter up in the air? Okay, with peanut butter smeared on one side and no peanut butter on the other side. Do you think this is uniform or non-uniform? Again, let's take a look at the possibilities, which is the sample space. It can land with the peanut butter side down or the peanut butter side up. Do you think this is uniform or non-uniform? Hopefully you guessed that it was non-uniform. Okay, why? Again, because there isn't an equal chance of it landing on the peanut butter side up or the other side. In fact, kind of like the coin, you should be thinking, well, it's more likely to land with the peanut butter side down because it's heavier, so it's going to be drawn to land first. So again, it isn't an equal chance of it landing on any of the outcomes, so for that reason, it is non-uniform. But is there a way to make it so that it is a uniform probability model? There is. You can simply add the equal amount of peanut butter on the other side, or simply remove the peanut butter from that one side. So do you know the probability of it landing on the other side? No. The only way would to be conduct many trials of the experiment, and that would be your way of approximating the probability. Okay, let's look at our last example. What about tossing a thumbtack in the air and having it land on the ground? Do you think it's uniform or non-uniform? Again, let's take a look at the sample space. It can land with the tack side up or the tack side down. Hopefully your answer was it's definitely non-uniform. Okay, why? Again, because it's not an equal chance of it landing with the tack side up or down. Again, it goes back to that weight. Definitely one is more likely to happen. So I wouldn't say it's an equal chance, therefore I wouldn't say it's uniform. But is there a way to make it so that it is a uniform probability? Well, I would say yes, but it wouldn't look like a thumbtack anymore. Okay, you would either have both ends looking sharp or both ends with this push part. So yes, but it wouldn't look like a thumbtack anymore. So do you know the probability of it landing on either side? The answer yet again is no, we don't. The only way to determine that is by doing many trials of the experiment to approximate the probability. So you're going to find that a lot with non-uniform probabilities is we don't know, and the only way to determine it is by doing a lot of experiments. So here, pretend we did conduct a couple of experiments, and this is what we had. Is it the tack side down or the tack side up? Here, according to the experiment, we actually see that it was more likely for the tack side up to occur. Like this. Okay, so that is according to our experiment. So coming back to spinner B. This spinner is an example of a non-uniform probability. Why? Because all the outcomes are not equally likely to occur because one is more likely to occur than any of the numbers here. Why? Because it's twice as large as 3, 4, 5, 6, 7, or 8. So since section 3, 4, 5, 6, 7, and 8 are equally likely, and section 1 is exactly twice the other section, we can find the probability of this non-uniform model. So let's imagine it was still cut like so. Okay, we can say there are 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. So the chances of me spinning and landing on a 1 would be 2 out of 8. So that's a quarter of the circle. The probability of a 3 would be a 1 out of 8. The probability of a 4 is 1 out of 8 because there's only one section out of the total of 8. The probability of a 5 is 1 out of 8. The probability of a 6 is 1 out of 8. The probability of a 7 is 1 out of 8. And the probability of 8 is 1 out of 8. So hopefully you can see there that this is definitely twice as likely as the other 1, 2, 3, 4, 5, 6 other options. Okay, so let's take a look at this math problem. We probably don't know how to get the answer. So what if you decide, okay, I'm just gonna guess out of the 5 options, okay? Is this a uniform or non-uniform probability? Well, assuming you don't know how to do this problem, you obviously don't know what you can cancel out or what you can include. So we're gonna say that this is a uniform probability, okay? We might choose A, B, C, D, or E, and we're as equally likely to pick any of these, especially since we don't know how to do this problem. So it is considered a uniform probability because there is an equal chance of you guessing the correct answer. So by the way, the correct answer is D, which is 4. Okay, so here, in the game of darts, players throw darts at a circle divided into 20 wedges. That's important to know. In one variation of the game, the score for a throw is equal to the wedge number that the dart hits. So if the dart hits anywhere in the 20 wedge, you earn 20 points for that throw. So for example, this is a 20 wedge. If you land anywhere in this wedge, you would get 20 points. Now, if you are equally likely to land on any wedge, what is the probability you will score more than 12 points? Well, let's remember. It's out of 20, right? Because there are 20 different wedges. And they're asking us for more than 12 points. Now, one important thing to consider is if it's more than 12, do we include 12 as part of the wedge? The answer is no, it has to be more than 12. So 18 would work, 13 would work, 10 does not work, 15 works, 17 works, 19 works, 16 works, 14 works, and again 12 does not work because it's not more than 12. So here I'm going to count them up, of course including 20 would be 1, 2, 3, 4, 5, 6, 7, 8. So it would be 8 out of 20, but guess what? We can reduce by 4, and that's going to give us a total of 2/5. So the probability that I'm going to score more than 12 points is 2/5 because there is a total of 8 wedges out of the total of 20 that will give me a score higher than 12. So real quick, this is a uniform probability. Why? Because each wedge is equal sized. One wedge isn't larger than the other, so it's equally likely for me to land on any of these wedges. So it is uniform. And again, that probability was 2/5. Now, let's remember complementary events. Complementary events is basically the complement of event of the opposite event. Okay, what's the probability of the opposite event occurring? So if the probability of a storm on the weekend was 2/7, the probability of no storm on the weekend is, the complement would be 5/7. And we know this is true because they should add up to 1. Now this also occurs when you describe it using a percentage. So the probability of it raining is 30%. The probability of it not raining is 70%. So here you're going to notice that it adds up to 100 instead of 1. Okay, so using these examples, if I asked you, are these events uniform or non-uniform? Hopefully you would say they are non-uniform because both are not equally likely to occur. It's more likely for it not to be a storm in the weekend, and it's more likely for it not to rain. So the following table shows a probability for a certain probability model. Is this probability model uniform or non-uniform? So taking a look at this, you should be saying it's uniform if they're all equally likely to occur, and it's non-uniform if it's not equally likely to occur. So take a look at the different probabilities. Hopefully your answer is non-uniform. Why? Because obviously all of them are not equally likely to occur, okay? And since the denominator of each probability are 12, what does this tell you about the model? Well, it basically means there are 12 total numbers in the bag, or a multiple of 12. Why would I say a multiple of 12? Because what if, the numbers were reduced? Obviously, it wasn't here, but it could be, so consider that. So which outcome is more likely? Hopefully your answer is 5, because it's a 5 out of 12, when the other ones were only 1 or 3. So again, it is 5. That's the most likely outcome to occur. In this non-uniform probability model, find the following. What's the probability of it landing on a 3? What's the probability of it landing on an 8? What's the probability of getting a number less than 8? What's the probability of getting a prime number? And what's the probability of getting an even number? I'd like you at this point to go ahead and pause the video and give it your best shot. Okay, so let's see how well we did. The probability of a 3 is determined right here. The probability of getting a 3 is 3 out of 12, but let's remember we always want to reduce whenever possible, and in this case I can. I'm going to divide both the numerator and denominator by 3, leaving me with a 1/4. Okay, the next one is what's the probability of getting an 8? Well, let's see. There are no 8s here, so I'm going to go ahead and say it's a 0 out of 12. Which reduces to just 0. I notice a lot of my students like to leave it at 0 out of 12, but please reduce that down completely to just 0, which we know 0 means impossible. It's never going to happen. Okay, now what's the probability of it being a number less than 8? Well, 2 is less than 8, 3 is less than 8, 4 is less than 8, 5 is less than 8, 6 is less than 8, and 7 is less than 8. So here, it would mean 1/12 for the 2, 3/12 for the 3, 4/12 for the 4. Whoops, put the wrong number there. 1/12 for 4, 5/12 for 5, 1/12 for 6, and 1/12 for 7. If you add these up, you'd end up with 4, 5, 10, 11, 12. 12 out of 12, which reduces to 1, which means this is a certain probability. It's definitely going to happen. Okay, now what about a prime number? Okay, so what is a prime number? A prime number is a number whose only factors will include 1 and itself. So prime numbers would include 2, 3. It wouldn't include 4 because 4 has a factor of 2. 2 and 2 makes 4, so it's not just 1 and 4. 5 is prime, 6 is not prime because you can make 6 by using 2 times 3. And 7 is prime. So for those reasons, I'm going to go ahead and add the different possibilities, which is 1/12 for 2, 3/12 for 3, 5/12 for 5, and then last but not least, 1/12 for 7. So I'm going to add these up. This is 4, 9, 10, which is 10 out of 12, which we can reduce by 2. And that's going to leave me with 5, 6. So it's pretty likely for you to pull a prime number. Okay, now last but not least, let's go ahead and find the probability of us getting a number that is even. So that's going to include 2, 4, 6, and that's it. So I'm going to go ahead and add the different probabilities, which is 1/12 for 2, 1/12 for 4, and 1/12 for 6, which is going to give me 3/12. I'm going to reduce the numerator and denominator by 3, and that's going to leave me with 1/4. Now, as we're doing this, we could have also considered the complement. So let's go back here. They asked us for the probability of getting a number less than 8, so the complement would be getting a number more than 8. So that would have been none. So what's the complement of 0? It would be 1. So here, what's the probability of getting a prime number? Well, you could have done the complement of getting the probability of a composite number, and you would have counted the probability for all the composite numbers. Now, why is this helpful? Because sometimes counting a lot of them would be tedious. So you might want to do the complement because it might be easier to calculate and simply find the complement that way. So it is helpful in certain occasions. So that is going to conclude the lesson for today. Thank you so much for tuning in, and as always, until next time, bye!